Yeah. Yeah.
So I have a topic, maybe
Yes.
naturalness in physics. What
Yes.
do you think?
Beats me.
Also related to some works of Sophie.
Yeah. Well, I mean, but the thing is that what's kind of annoying is that it's not a philosophy problem. Okay. So this is a topic that, and it's not remotely just these books. Even a lot of professional particle physicists, but who are not model builders, severely misunderstand this, and partially because it's been sometimes explained in a poor way. But there's a very concrete problem. There's a very concrete, sharply defined problem, which is just the following. So, really great physicists, people like Sidney Coleman, for example, never really bought naturalness. Sidney would often say that, who cares? It's just a parameter. You measure it from nature and you're done, like everything else. There's no problem with the fine-tuning is in your head, right? And even really great people, truly great people like Weinberg had that attitude for a little while in the 70s, until you try the following concrete problem, which is you imagine that you try to construct the theory where you can actually calculate the Higgs mass squared parameter, okay? Not just take it from experiment. Just imagine there's a more complete theory where you can calculate it. Now, forget the issue of naturalness altogether. Totally forget it. Just try to find a theory where it becomes calculable. Just so you can even calculate the sign, never mind the magnitude, okay? Now, that's already a tall order, okay? You can't just roll out of bed and find theories where you can calculate the Higgs mass squared starting from some theory that doesn't have those dimensionless parameters. And what people have found in the 30 years, 40 years that they've tried to do it is that every such theory has the feature that now when it's calculable as a function of a bunch of dimensionless parameters of this deeper underlying theory, that you never get the Higgs alone, unless you now choose these dimensionless constants to be within the usual 1 part in 10 to the 20, 1 part in 10 to the 30 of each other, okay? That's how people practically and concretely started realizing there was a problem. And I was telling this story maybe, I forget when, over dinner at some point earlier today, that many of us ran into this sort of little version of the hierarchy problem associated with supersymmetry, other theories, where already being compatible with experimental limits from the 90s, from the mid to late 90s, was forcing these theories to be fine-tuned, okay? And all of us who studied this problem have their own stories of the version of what I'm about to tell you. But when I was a grad student, I was working on some project with my advisor involving supersymmetry breaking and models and all this stuff, and I was the person charged with the grunt work of figuring out all the experimental limits and flavor change neutral currents and this and that. I did all that stuff, and at the end I had to find numbers that actually worked. So I was spending an entire night searching around in the parameter space on the computer, and it just kept not working unless I dialed this parameter and that parameter to like % level accuracy. And I went to my advisor and said, what the hell is going on? And he said, oh, that's kind of confusing. And it started dawning on us that there was some tuning in supersymmetry already. Not a part in a million, but these sort of part in 50 kind of tunings. There was another funny story with my former student, Jesse Thaler. We were doing another project together where it was about, anyway, simulations for, collider physics simulations for LHC data. And and it was very computer intensive, and so we had borrowed, Jesse had borrowed a big part of the cluster associated with the Center for Astrophysics at Harvard. So he was running versions of the MSSM on the computer, and he was putting in all the experimental constraints just to make sure we're talking about something that worked out right, including that the mass of the Higgs had to come out heavy enough, but that everything worked. And then he came like in the middle of this week and said, I don't know what's going on. It's just so slow. It's taking so long to find anything. I don't know why. It's cycling through zillions of examples. And it turned out it's because he had put in, especially the experimental constraint, the Higgs mass comes out, right? And so you needed to run a factor of 100 more models than you had thought you needed to in order to find one where the stops were heavy enough and everything tuned enough for it to work. So that's how he discovered the fine-tuning problem of supersymmetry, because he was using a factor 100 more computer time than he needed to in order to do our simulations, okay? So this shows that in a concrete theory where you can actually calculate, you find what it takes. That if you try to separate the Higgs off from everyone else, it starts needing very fine parameter choices, okay? So this means that it's not just philosophy or bullshit. First you have to do some job to be able to calculate the Higgs mass squared to begin with. And when you can do that, you can see in that theory or not, maybe some miracle would happen. Maybe there is some like wonderful identity that collapses the coefficient of the Higgs mass squared to a tiny number. We can't prove those possibilities abstractly. Maybe it could happen. So saying that there's an issue with naturalness is more a statement of the 30 years of trying this that we've done so far. And every example we've found so far has this feature, that all the dimensionless numbers that come out in front of the Higgs mass squared are order 1. And so, unless we do absurd adjustments of the parameters, it doesn't work. So that's just truth, okay? Could it be there's some other model that has some miraculous number theory identity or something which makes it come out right? Maybe there is. If you find it, it would be revolutionary, right? So no one is saying that that's not possible. And that's why no good person has ever said naturalness is a law of nature. Never has been a law of nature. It's at best been a guide for what to expect. But taken as a guide for what to expect, it has also worked many times in the past, okay? And actually in the recent past, in the last 100 years, there are 3 separate times that it worked kind of spectacularly well. If you go further back in the past, there have been times that it failed spectacularly as well. So, you know, it's like anything. You can't be, it's not a principle, it's not a law. It's kind of it's a guide for what to think about. And you should be open to the possibility that it's a good guide and that it's a bad guide. But on top of that, it's not like, you know, people thought about things and they liked supersymmetry because it was elegant and they liked the Brian Greene's violins and stuff like that, right? But nothing to do with that. It's that you believe in naturalness, you believe in supersymmetry. It leads you to predict, you should see superpartners at the weak scale. Exactly those particles you put in to the RGEs to run the gauge couplings up to high energies and they meet the percent level accuracy. No reason that had to happen. I mean, this is not the kind of gift that like lands in your lap every day of the week. This is not something to be like pissed on, right? It's not like we have so much clues from nature that we can just ignore things that work for without any like tuning of any knobs or anything. You take the dead simplest version of the supersymmetric theory, you run up the couplings and they meet to percent level accuracy. Where do they meet? Not at a crazy place, you know, within a few orders of magnitude of the Planck scale, but slightly lower than the Planck scale so that you don't have to worry about higher dimension operators messing up unification. I mean, that's another accident. Apart from the percent level accuracy, they're running logarithmically. They could have met 20 orders of magnitude above the Planck scale, 10 orders of magnitude below. They meet right around where you expect gravity to get strong and join all the other forces. And right around the scale of the neutrino masses, and right around the scale that you expect to associate with inflation. These are not, I mean, this is, I think it was remarkable a long time ago, it continues to be remarkable today. Did we interpret it correctly? Maybe not. Is it a red herring? Maybe. Did people sit around saying, we're damn sure what's going to go on because of this one numerical fact? Of course not, okay? I don't know any like serious person who was totally sure it was obviously all correct, especially because the whole time it's had these circumstantial things going for it, and there's been circumstantial things going against it from day one. We could have seen electric dipole moments, we could have seen flavor-changing neutral currents, there could have been all kinds of indirect hints for the presence of superpartners that were not there. And more importantly, there could have been direct evidence for them already in the 90s, already in the 80s even. Okay? This was supposed to be theory of the weak scale of particles at 80 and 90 GeV, not a TeV. So even saying that they should have been at the TeV scale is wrong. They should have been at the 100 GeV scale. And there's a reason why The theories that were popular in the 80s and 90s had like leptons at 50 GeV, squarks at 200 GeV. That's where they should be. Okay? There's no reason for them to be 10 times heavier. So I don't know any good person who was like, oh yeah, naturalness is obviously right, and we might as well not even do the experiment and go home because it's so obviously right. There were idiotic people who said things like that. And they said things like that because their stature in the field was really low, and this was a way to seem like super confident and get some like version of the expected glory when it came. Because they wanted to say, even though I had nothing to do with the invention of this idea. See, the people who invented the MSSM, Savas Dimopoulos, Howard Georgi, the people who invented the concept of naturalness, Wilson, okay? All of these people have been nervous about it. And I can say that for myself, what broke things for me pretty decisively was around 10 years ago when Savas and I stumbled into Split SUSY. Split SUSY for me solved all the problems, and it still solves all the problems. And if you woke me up in the middle of the night and put a gun to my head, I think it's probably Split SUSY is the answer. Okay? Because every clue of the last 30 years means something in that picture of the world. Okay? So why did unification work? Because it's supersymmetric unification, pretty much. There's just this little detail at the end about this order alpha splitting in the spectrum. Is the order alpha splitting crazy? No, it's never been crazy. People always had to work to make the gauginos and the scalars degenerate because you have to break more symmetries to get the to give the gauginos a mass. You have to break R symmetry and supersymmetry. It was the earliest models. The easiest thing to happen is to have a one-loop splitting between them. Why were people so obsessed to bring them comparable? Because of naturalness. If you have a picture, there might be a landscape, something else. Is it conceivable that factors of 1 part in 10,000, 1 part of 100,000 are chump change compared to 1 part in 10 to the 120? Yes, it's very conceivable that that's true. Little detailed things. In that picture of the world already back in 2004, we made a prediction that the Higgs mass should be between 120 and 135 GeV. That's a little 15 GeV window. Bang in that window, right? It didn't have to be, so it doesn't mean that it's right. But 99% of models people talked about before the LHC are already falsified. This is one of the very few that's not dead yet, okay? And it actually made one small prediction, which is actually correct. Now, who are the people talking about this? I had just come out of talking about the most extreme version of naturalness possible, which was that all of quantum gravity hits you over the head at the TeV scale. My collaborator had given the world the standard paradigm of the MSSM, and who are the people who are ready to chuck it? Us two were ready to chuck it. And what was the reaction of most of of some part of the community? They yelled at us at conferences. I mean, I was literally yelled at. It's not a joke. I gave a talk about Split SUSY and people literally yelled at me, saying that this was cheating, it was giving up. I mean, it was unbelievable the amount of emotion they had about this. And again, ironic, because the people who are at least entertaining ditching it had done more to give the world theories of natural electroweak symmetry breaking than any of these guys. So it's an interesting psychological thing. The people who made the most noise had almost nothing to do with the invention of any of the relevant ideas, and it was their way of trying to attach themselves in some way to the perceived glory of discovery when it actually happened. In doing so, they both fucked themselves over, and they gave this perception to people who are pretty far outside the field of what was actually going on. So anyway, I'm still conflicted about naturalness. I don't know what it means. It still bothers me that it's been so successful in the past. It's true that it's badly unsuccessful for the cosmological constant. It's true that the Higgs might be somewhat like the cosmological constant. It could have also been some much more dirty, detailed thing about particle physics, and it's always seemed like somewhere in between to me, and I still don't know where it comes down on the spectrum. If I had to guess today, you put a gun to my head, I said I think it's Split SUSY. I think it's probably split, but I'm not super confident in it. I mean, it's passed a few of these tests. There's a few other small things, like there's this famous, little discrepancy in supersymmetric gauge coupling unification, that when you really work it out accurately at 2 loops, you make a prediction for alpha S at MZ that's around 0.128. And
triangle, right?
yeah, that's right. Yeah, no, I mean it's very. I mean, people misinterpret that and say, oh, it looks like just like a 10% thing. But no, there, as you say, there's a two-dimensional plane in alpha s and sine squared theta, and it's really damn close to a line on that plane. But still, in detail, the two-loop corrections move it a little bit in the wrong direction. That people used to want to fix up by having a biggest threshold near the gut scale. But in split SUSY, you accomplish that with the biggest threshold near the weak scale. Okay? And that, so there's a generic prediction for alpha s at mz around 0.115. Okay? And that's pretty good. It's 118 is the right answer. It's a pretty good. So the little detailed things also work. So I don't know, I think that, and it's also been true that in that picture, in sort of, it's hard to quantify, but in sort of half of the parameter space, the LHC would have discovered the gluino, and half it doesn't. It depends on whether the WIMPs are a 3 TeV Wino or a 300 GeV well-tempered neutralino, right? Depending on which one it is. And this is not something we're saying now that the LHC hasn't seen something. I wrote papers in 2006 where I said, this is what we think is going on, and these are the two options, and either the LHC will see it or it won't. And it's not something, unlike natural theories where it had to see it, here is just a 50-50 proposition. So, that's why I'm saying, I'm not like smashed over the head by LHC results. It looks pretty much like, it's not shocking to me at all. But it won't be shocking if you're paying attention to the data. And well before people like me, people like Riccardo Barbieri, were saying this already starting from the mid-90s. It was not a popular thing to say back then. But always saying, look, these things are overdue. We should have seen them already. What's going on? And more people started paying attention to him. And the reason, to me, split was psychologically important is that you could always say, yeah, but this is all niggling stuff. And anyway, why would all the stuff with unification and dark matter, all the rest of it, work so well if it was tuned? And there was always this idea that the choice was between supersymmetry and just a standard model all the way up to the gut scale. And between the two of those, well, one of them loses unification and is horribly tuned, and the other one has unification and dark matter and isn't tuned. And splits the difference, right? It has unification and dark matter. It's somewhat tuned, but then, but you're not completely forgetting about the elephant in the room of the cosmological constant. And I don't know. I think to me, it's the right. If there's something about it that's felt right from day one. Certainly, if you look at my research, I stopped building models for the weak scale from that point on because I thought this is probably right. And I only returned to doing it when prodded by data, anomalies that may or may not go away, but not from a belief that other kinds of models were needed. So, and that's just my own story. If you talk to like many other model builders, they'll have, I think, the professional model builders, people have thought about these things for a long time, have a very sober attitude about it, and they certainly never had this religion of naturalness that, oh my goodness, you can't even imagine anything else. Like I said, Steve Weinberg, another one of the people who gave the world Technicolor, right? Steve Weinberg introduced the anthropic idea for the cosmological constant. So it's the people who actually solve the problems who entertained radically different possibilities. And anyway, it's a little bit unfortunate that the people who solved nothing, but who wanted to be seen as champions of the thing that was right in the end, I think caused a little bit of confusion.